guys, this is the fourth video in chapter 3, the video on stoichiometry. Now, stoichiometry sounds like a really scary term because it's big and it's something you probably don't know what it is. But really, stoichiometry, all it means is the comparison of elements or compounds in a chemical reaction. So let's take a look at an example using something that you can relate to. The making of delicious pancakes. So here we have the pioneer woman's ingredients for pancakes. And so let's take a example here. Okay, so say you went to the store and you got all of this stuff except for you forgot milk. You forgot to pick up the milk, and you have, half of a gallon left, or maybe a little bit less than. You've got 4 cups left, but you got all the rest of the stuff. So using all 4 cups of milk, how many pancakes could you make? Well, of course, you can make, if this whole thing makes 6 pancakes, doubling the recipe and including 4 cups of milk would make 12 pancakes, right? But what you did was you said that for every 2 cups of milk, because that was what we ran out of, right? We ran out of milk. So 2 cups of milk makes 6 pancakes, right? That was our conversion factor. So if we had 4 cups of milk, we would make 2 cups of milk makes 6 pancakes, right? And so we have 4 divided by 2 times 6 would give us 12. And that's what you did in your head. Now, this right here, this is a conversion factor that compares one thing to another. If used in chemical reactions, this is called a molar ratio, and that is really the only step that's different from the normal conversions we've done all chapter 3 and stoichiometry. Let's take a look at an example with an actual reaction. So here I've got the combustion of propane, again, hydrocarbon, oxygen, carbon dioxide, and water. And so here we see that 1 molecule of propane produces 3 molecules of carbon dioxide. And so let's write that down. So 3 molecules of C3H8 make 1 molecule of C3H8 makes 3 molecules of CO2. Now, remember, in the first video that we talked about and the second video, these molecules are also moles, right? And we also can say we have 1 mole of propane. And if we had a mole of propane, that means we'd have to have 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. And so all of these can be molar values as well. So yes, it relates the molecules, but because Avogadro's number in a mole is just a collection term, these also relate molar values. And so this also means that 1 mole of propane, C3H8, makes 3 moles of carbon dioxide. Cool. That's the only big idea here, guys. It's super easy. So if I had a conversion factor that I needed, I could pull it from this. I could say, 1 mole of C3H8 and 3 moles of CO2. And so if I started with 4 moles of propane, I can put in my conversion factor here for every 1 mole of propane. I form 3 moles of carbon dioxide. Moles cancel, giving me 12 moles of carbon dioxide form. This is the only idea. This is the only addition to the normal conversions we've already done from that constitutes stoichiometry. That's the only thing that's really new. And we're going to throw all this together. It's going to seem kind of big, but it's all just the same stuff. This right here, this is the big idea. This is the molar ratio. And since we're going from moles to moles, we can do stuff with moles, right? We can convert to mass, and we can convert to molecules. So that's what we're going to do. Mass is the big important one, and it's kind of cool. especially for us, because we can start to see how it's so useful in chemistry in general. Because I can say, okay, we're working with moles at the moment on the slide, but I can say I put in, 85 grams of propane, and I want to know what mass of water I should get when I burn it. We can do that, right? Because we just go from moles to moles, and we can convert to mass. Now, how do we do that? That's called mass-to-mass stoichiometry, and I'm going to look at a general outline, and then we're going to do an example together. So here's the general outline. We've got a reaction, A goes to B, right? So here's our reaction. And so the first step, if I'm given mass of A, I have to convert it to moles first, so divide by the molar mass to get moles of A, and multiply by the molar ratio. Molar ratio, that's it. That's, again, the big idea here. It's a comparison of moles of one thing to moles of another. It's how we convert unit-wise from one compound to another compound in a reaction. And we're going to do moles of B over moles of A, moles of what we want over moles of what we were given. Once we're in moles, then we can convert to mass if we need to, or molecules, or whatever. We have to go from there. So if we're converting to mass, we multiply by the molar mass to cancel out that molar value there. But again, this is huge for a chemist. This is huge. This is a huge idea, because we can look at a reaction, look at how much we put in, and look at how much we get out. To give you an idea, so I've got this reaction, the combustion of octane. Once again, remember our one of my favorites. Everyone likes blowing stuff up. So in my car, it's a tiny little car, and I've got about, this is, kind of just ballpark, 10,500 grams it's actually about 15 liters of a gas tank. And assuming all of gasoline is octane, which it is way not, but just making that assumption, we have about 10,500 grams of octane that I put in there. If I just put in straight octane, that's the mass of octane that I'd have in. And being a environmentally conscious individual, I want to know what my carbon footprint, what's my mass of carbon dioxide that I dump out into the atmosphere whenever I drive on a full tank of gas. So how do we do that? Well, I've got my 10,500 grams of octane that I start with, and then we can pull down our molar mass of octane, which, if we look on the periodic table, we have 12 grams for carbon, and so we multiply that by 8, and then we add, so we can go all the way out if we want, times 8 plus 1.00, well, not 10, 1.0079 times 18. So we've got 114.2 as our molar mass, so let's put that in there. So 114.2 grams of C8H18 in 1 mole of C8H18. And so now comes the big idea, the big molar ratio. And remember, the molar ratios come from the balanced chemical reactions, the coefficients from the balanced chemical reaction. And so if I want to know how much carbon dioxide I get, I have to pull out these two numbers here. Okay? I have to pull out those two numbers right there. And this is where writing down the full units is super important, because if I just put in, if I had 1 mole and I had, 16 moles and 2 moles, well, it looks to me like those cancel, and I'll get the wrong answer. But if I write out mole of octane, I can see that 2 moles of octane, C8H18, produces 16 moles of carbon dioxide. And for these stoichiometry reactions, guys, we don't have to compare reactant to product. We can see how much oxygen I need to react with 10,500 grams of octane. It's the same idea. We convert to moles first, and then instead of 16 moles of carbon dioxide is produced from 2 moles of octane, it would be 25 moles of oxygen are needed to react with 2 moles of octane. Then the very last step, we convert to we convert to mass, 44.0 grams CO2 in 1 mole of CO2. Moles cancel, moles of carbon dioxide, moles of octane cancel, grams of octane cancel, and we can plug this into our calculator. Once we have all this done, we have 10,500 divided by 114.2 times 16 over 2, which is 8, and then multiply that by 44, and I get 32,000. So I get 32,000, keeping in mind significant figures, 32,400 grams of carbon dioxide. 3 sig figs right here, 3 sig figs right here, all good. So 32,400 grams of carbon dioxide is produced for whenever I drive around in my car. So we can do these conversions, and it's really nice because we can actually, it's one of the coolest things to be able to just look at a reaction on a piece of paper and say, okay, if I put this much in there, I'll get this much out. It's exciting and it's neat, and we'll do a lab over it. Yeah, so that's the review over stoichiometry. I'll see you guys next time whenever we do some more problems with stoichiometry, including percent yield, limiting reagent, and theoretical yield.